Milankovitch orbital variations shape Earth's climate, and Earth's ice ages are cyclical events that have occurred for thousands of years. However, until relatively recently, it was not known exactly what caused these cycles or how they occurred. Today, we understand that these cycles are related to Milankovitch orbital variations or cycles. But exactly how do these cycles work, and what produces them? Can the Milankovitch cycles help us predict how climate change will behave in the future? Stay with us to find out. What are the Milankovitch orbital variations, also known as the Milankovitch cycles? These periodic variations in Earth's orbit and orientation influence long-term climate and are closely related to glaciations and interglacial periods. These variations are described in terms of changes in the eccentricity of Earth's orbit, i.e., how far away or how close it is to the Sun at different times during its orbit, variations in obliquity, the tilt of Earth's axis, and changes in precession, the orientation of Earth's axis of rotation. These changes also cause shifts in the dates of the equinoxes. These orbital variations were first introduced by Serbian engineer and mathematician Milutin Milankovitch, who in the 1920s, through detailed mathematical analysis, proposed that these orbital variations could be responsible for climate changes on a scale of thousands of years, especially concerning ice ages. Milankovitch used precise astronomical calculations to model how variations in Earth's orbit would affect the distribution and intensity of solar radiation reaching different parts of the planet, which would, in turn, influence global climate. Milankovitch drew on the laws of planetary motion formulated by Johannes Kepler and perfected by Isaac Newton, using a mathematical approach to predict how fluctuations in Earth's position relative to the Sun would affect insolation at different latitudes. His work combined knowledge in astronomy, mathematics, and physics to build a model that could explain the patterns observed in the geological records of past glaciations. Although the scientific community initially ignored the idea, time eventually proved Milankovitch right, and today the importance of these cycles in understanding long-term natural climate changes is widely recognized. To better understand the Milankovitch cycles, we must first understand what orbital elements are. Orbital elements are parameters that describe the shape and orientation of the orbit of one celestial body around another, such as a planet around the Sun. These elements determine how the distance and inclination of the body in its orbit vary, affecting the amount and distribution of solar energy it receives. In astronomy, a celestial body can have up to 7 orbital elements. However, to understand the Milankovitch cycles, it is sufficient to focus mainly on 3. Eccentricity refers to the shape of Earth's orbit around the Sun, which varies from being more circular to more elliptical over a cycle of about 100,000 years. When the eccentricity is high, the difference between the maximum and minimum distances from Earth to the Sun is more significant. When the eccentricity is low, the maximum and minimum distances from Earth to the Sun are not so great. In other words, when the eccentricity is high, the maximum and minimum distances from Earth to the Sun are more significant, and the orbit is more elliptical. This causes solar radiation received by Earth to vary significantly throughout the year. In contrast, when the eccentricity is low, the orbit is more circular, and the amount of radiation Earth receives does not vary as much throughout the year. In short, this cycle affects the variation of radiation Earth receives, which influences the intensity of the seasons and contributes to the beginning and end of ice ages. Obliquity refers to the angle of inclination of Earth's axis relative to its orbital plane, and it varies between 22.1 degrees and 24.5 degrees over a cycle of about 41,000 years. This angle determines the severity of the seasons. A higher tilt angle causes colder winters and warmer summers in both hemispheres, while a smaller tilt angle reduces this seasonal difference. Obliquity directly impacts the distribution of insolation, especially at high latitudes, and thus plays a key role in the formation of glacier. Precession is the slow, gradual movement of Earth's axis of rotation, similar to the wobble of a spinning top, with a cycle of about 26,000 years. This motion changes the orientation of Earth's axis in space, which affects the timing of the seasons during Earth's annual orbit around the Sun. Precession is crucial in determining the intensity and duration of the seasons in different parts of the globe, as it modifies the dates on which the equinoxes occur, thereby affecting when the seasons begin and end. Together, These three orbital elements generate complex patterns of climate change that manifest over tens to hundreds of thousands of years. The variations in insolation caused by these cycles drive long-term climate changes, including transitions between glacial and interglacial periods. The Milankovitch cycles are fundamental to understanding Earth's climate fluctuations over the last few million years. These cycles directly influence the amount and distribution of solar radiation Earth receives, affecting global temperatures, precipitation patterns, and glacier formation. Ice ages, prolonged periods of cold weather with significant expansions of ice sheets, are closely linked to the Milankovitch cycles. During periods of low eccentricity, lower obliquity, and when precession aligns the northern hemisphere winter with when Earth is farthest from the Sun, conditions are favorable for ice accumulation at the poles. The analysis of ice cores and marine sediments provides an example of how this relationship has been measured and studied. Scientists such as James Crow and later Milankovitch worked on the theory of orbital forcing, which holds that changes in Earth's orbit are a critical factor in initiating ice ages. More recently, researchers such as André Berger of the Catholic University of Louvain have been instrumental in modeling the impact of the Milankovitch cycles on climate. Berger refined Milankovich's calculations and developed climate models linking orbital variations to global temperature records obtained from ice cores in Greenland and Antarctica, as well as ocean sediments. These records coincide with those of the European Antarctic Ice Core Project, EPICA, where researchers obtained data showing how the Milankovitch cycles relate to glacial and interglacial periods. This confirms that changes in solar radiation due to orbital variations have been a significant factor in climate changes over the past 800,000 years. Although the Milankovitch cycles provide a compelling explanation for many aspects of natural climate change, certain discrepancies and challenges have arisen in correlating these cycles with observed climate records. The two most prominent are the Middle Pleistocene transition and the Stage 5e paradox. One of the critical challenges in Milankovitch theory is the so-called Middle Pleistocene transition, a change in glaciation patterns that occurred about 1 million years ago. Before this transition, glacial cycles followed a 41,000-year pattern, coinciding with the obliquity cycle. However, after the transition, they changed to a 100,000-year pattern, aligning with the eccentricity cycle. Although eccentricity has a smaller effect on received solar radiation than obliquity, Milankovitch theory does not fully explain this change, suggesting that other factors, such as ice sheet dynamics or atmospheric composition, e.g., CO2 concentrations, could play a crucial role in modulating Earth's climate. Another discrepancy is the well-known problem of Stage 5e, an interglacial period about 130,000 years ago. According to models of the Milankovitch cycles, this should have been a period of colder weather. However, geological evidence indicates that it was one of the warmest interglacial periods of the last 500,000 years, with global temperatures higher than today. These discrepancies have led to a reassessment of how Milankovitch cycles interact with other climate system components such as ice sheets, vegetation, and oceans, and how these interactions can amplify or attenuate the effects of changes in solar radiation. The principles of Milankovitch orbital variations are not limited to Earth alone. In fact, these cycles have also been observed and studied on other planets in the solar system, providing a broader perspective on how orbital dynamics may influence planetary climates. Mars is the planet that most closely resembles Earth in terms of susceptibility to orbital variations due to its axial tilt and fluctuations in its elliptical orbit. Changes in eccentricity, obliquity, and precession on Mars have significant effects on its climate, similar to what happens on Earth. The red planet experiences changes in its obliquity more pronouncedly than Earth. While Earth's obliquity varies between 22.1 degrees and 24.5 degrees, on Mars, this tilt can range from 10 degrees to 60 degrees over millions of years. These drastic variations in the tilt of the Martian axis profoundly influence the distribution of the polar ice caps and the stability of water reserves on the surface. During periods of high obliquity, Mars' polar ice caps can shrink significantly, redistributing ice to lower latitudes. The study of stratified deposits in the polar regions of Mars has provided evidence that the Milankovitch cycles played a key role in their formation. This suggests that these orbital cycles, as on Earth, influence the planet's climate over long periods. The Milankovitch Orbital Variations offer a fundamental key to understanding how Earth's climate, and the climate of other planets, change over time. These cycles, which include variations in eccentricity, obliquity, and